Okay, so now let's try to understand a little more what quantum algorithms and quantum circuits look like. Okay, so what's our basic model of computing? Well, our basic model looks like this now. So we have n qubits, okay, which are initially, let's say, in the state 0. These we think of as the inputs to the circuit. And what I draw here, these lines, these are wires, and each wire carries a qubit of information. So let's think of each of these wires as our electron in the hydrogen atom, whether it's in the ground or excited state, or in a superposition of the two. And of course, as we go along, these wires will get entangled, the qubits get entangled. Okay, now what do we actually do? Well, a quantum circuit is a sequence of gates. So it consists of a sequence of gates. So you might have some kind of quantum gate that acts on these two qubits and outputs 2 qubits. There could be also single qubit gates. So this might be the Hadamard, this might be Z, whatever, right? So there are some sort of gates. This might be a control NOT. We don't know. Okay, but a quantum circuit is just a sequence of gates. Maybe this one just goes right through. Perhaps there's another gate here, etc. So quantum circuit consists of these n wires that just go through from left to right all the way to the end. And then maybe there are other gates back here. This whole thing is called a quantum circuit. These are the outputs of the quantum circuit. And now what we might want to do is we might want to measure these bits. We either, it could be that we only measure some of these qubits. So we select some of these qubits, maybe these ones, and we put in a measuring apparatus, and then as output we get a classical string. So that's a quantum circuit. Now, there's a question: what kind of gates should we allow in this quantum circuit? Well, so let's look at the corresponding question on the classical side. So if you have a classical circuit, what kind of gates should one allow? Well, there are many kinds of gates one can come up with: ands, ors, nots, etc., etc. But there's this very simple but very, very beautiful fact about classical circuits, which is that you don't have to allow for a very rich set of gates. In fact, all you need is a NAND gate. A NAND gate takes as input two bits and outputs 1 bit. It's the NOT of the AND, right? So the output is 1 unless x equal to y equal to 1, in which case the output is 0. So the claim is that no matter how complicated a circuit you're trying to create, you can always assume that your building blocks you have only one kind of building block, which is a NAND gate. Okay, so the way one says this is by, expresses this fact is by saying that the NAND gate is universal for classical computation. So now we can ask, is something like this true also for quantum computing? Is there a universal family of quantum gates? And it turns out that there is. So there are various families of quantum gates that are universal, but for our purposes, the gates that we saw, C0, Hadamard, X, Z, together with a pi/8 rotation. So if you have just these 5 types of gates, then the claim is you can implement any quantum circuit that you want. Okay, now let me say just a couple of more words about it to make this a little more precise for those of you who are interested. So what does it mean that this gate set is universal? So what we'd like it to mean is that, let's say that somebody came along and they said, there's this particular unitary transformation, there's this particular gate that I have in mind, and I'm going to, it's really quite magical. This gate has the property that it will simplify every quantum computation. You only have to implement this gate, and then, everything is going to be so much faster, you won't even believe it. Okay, and what does this gate look like? Maybe it takes as input 4 qubits, outputs 4 qubits, and implements some unitary U on these 4 qubits. So it's represented by a 16 by 16 matrix, complex matrix. Okay, so So now, the fact that these 5 gates are universal allows us to say, it cannot be the case that your gate, your favorite gate U could be that powerful, because it can't be more powerful than these, because what we'll show you is how to implement U using these 5 gates. And moreover, to implement U, we'll do it pretty efficiently. Okay. Now, there's one problem. We cannot, of course, implement U with perfect precision, because U, after all, is represented by a 16 by 16 complex matrix, and you need infinitely many digits to specify this to perfect precision. So instead, what we will do is, for any given epsilon, we'll implement an approximation U sub epsilon, which is epsilon close to U. And it turns out that if U is given by a D by D matrix, and you want to be epsilon close to the answer, the number of these elementary gates that we need scales roughly like, well, it has to scale like, it might be some polynomial in D, let's say, or the D squared times some polynomial in log 1 over epsilon. So certainly log cubed works, and maybe even, well, let's say log cubed, just to be on the safe side. So the dependence on D and epsilon is mild. Now, I claim that something like this dependence on D squared is really necessary, because just by counting argument, there are lots of unitary transformations which are D by D, and these are only 5 gates. So how can you express all of them unless you pay such an overhead? Okay, so what's the upshot of all this? The upshot of all this is, what we are claiming is, we are going to be implementing this circuit U sub epsilon, where if you look inside, what it consists of is C0 gates and Hadamards and X gates and Z gates and so on. And moreover, this circuit U sub epsilon behaves almost the same as U, in the sense that if you look at these two transformations, U and U epsilon, they are epsilon close in operator norm. So U minus U epsilon in operator norm is at most epsilon. Okay, which means that this is another way of saying that if you apply both of these circuits to the same quantum state, the state that results in the two cases, these two states are going to be epsilon close to each other in Euclidean norm.